Welcome to our deep dive into the fascinating world of gas laws. In this video, we'll explore the fundamental principles that govern the behavior of gases. Gas laws are essential in understanding everything from how balloons float to how our lungs work. These laws describe the relationship between pressure, volume, temperature, and the amount of gas. By the end of this journey, you'll see how these concepts apply to real-life situations and scientific experiment. Let's begin by setting the stage for our exploration and understanding why studying gas laws is so important in both science and everyday life. Before we dive into the laws themselves, let's clarify what a gas is. Gases are one of the four fundamental states of matter, alongside solids, liquids, and plasma. Unlike solids and liquids, gases have neither a fixed shape nor a fixed volume. Their particles move freely and spread out to fill any container. This unique behavior is what makes gases so interesting to study. Understanding the properties of gases helps us grasp why they respond so dramatically to changes in pressure, temperature, and volume. Now let's move on to the key variables that affect gases. Studying gases, there are four main variables to consider: pressure, volume, temperature, and the number of moles. Pressure is the force exerted by gas particles against the walls of their container. Volume is the space the gas occupies. Temperature measures the average kinetic energy of the particles, and moles represent the amount of substance. These variables interact in predictable ways, which is what the gas laws describe. Understanding these variables is crucial before we look at the specific laws that connect them. Start with Boyle's law, one of the earliest gas laws discovered. Boyle's law states that at constant temperature, the pressure of a gas is inversely proportional to its volume. In simple terms, if you decrease the volume of a gas, its pressure increases and vice versa, as long as the temperature remains unchanged. This relationship is fundamental in many scientific and industrial processes. Next, we'll see how this law is represented mathematically and look at some practical example. Mathematical expression of Boyle's law is simple. P times V equals constant, where P stands for pressure and V for volume. This means that if you multiply the pressure and volume of a gas at a constant temperature, the result will always be the same. For example, if you have the volume of a gas, its pressure will double. This equation is widely used in calculations involving gases, especially in laboratory settings and engineering applications. Imagine using a syringe. When you push the plunger in, you decrease the volume inside and the pressure increases, making it harder to push further. This is Boyle's law in action. The same principle applies to scuba diving, where changes in water pressure affect the volume of air in tanks and lungs. Understanding Boyle's law helps keep divers safe and is also crucial in designing medical devices and industrial equipment. Next, let's look at Charles's law. This law describes how gases expand when heated. Charles's law states that at constant pressure, the volume of a gas is directly proportional to its absolute temperature. In other words, if you heat a gas, it expands; if you cool it, it contracts. This relationship is vital in understanding hot air balloons and even the behavior of car tires in different weather conditions. The equation for Charles's law is Vt equals constant, where V is volume and T is temperature in Kelvin. This means that if the temperature of a gas increases, its volume increases proportionally, provided the pressure stays the same. This law is especially important in meteorology and engineering, where temperature changes can significantly affect gas volumes. A great example of Charles's law is a hot air balloon. When the air inside the balloon is heated, it expands, causing the balloon to rise. Conversely, when the air cools, the volume decreases and the balloon descends. This principle is also why car tire pressure changes with temperature. Understanding Charles's law helps us predict and control these everyday phenomena. Now let's explore Gay-Lussac's law. This law focuses on the relationship between pressure and temperature. Gay-Lussac's law states that at constant volume, the pressure of a gas is directly proportional to its absolute temperature. This means that as the temperature of a gas increases, so does its pressure, provided the volume does not change. This law is crucial in understanding how pressure cookers work and why aerosol cans can be dangerous when heated. The equation for Gay-Lussac's law is Pt equals constant, where P is pressure and T is temperature in Kelvin. This means that if you increase the temperature of a gas, its pressure will also increase as long as the volume remains unchanged. This law is especially important in safety protocols for pressurized containers and in understanding weather phenomena. Think about a pressure cooker. As the temperature inside increases, so does the pressure, allowing food to cook faster. Similarly, if an aerosol can is left in a hot car, the pressure inside can rise dangerously, sometimes leading to explosions. Gay-Lussac's law helps us understand and prevent such hazards, making it vital for both safety and efficiency. Combined gas law brings together Boyle's, Charles's, and Gay-Lussac's laws into a single equation. It shows how pressure, volume, and temperature are all related when the amount of gas is constant. The equation is P times V/T equals constant. This law is especially useful when more than one variable changes at the same time, which is common in real-world scenarios. Combined gas law is practical for solving problems where pressure, volume, and temperature all change. For example, if a gas is compressed and heated at the same time, this law helps predict the final state. It's widely used in engineering, meteorology, and even in calculating the behavior of gases in the atmosphere. Avogadro's law is another key principle in the study of gases. It states that at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of gas present. This means that adding more gas to a container increases its volume, as long as temperature and pressure remain unchanged. Avogadro's law is fundamental in understanding chemical reactions involving gases. The equation for Avogadro's law is Vn equals constant, where V is volume and N is the number of moles. This direct relationship means that doubling the amount of gas will double the volume, provided temperature and pressure are constant. This law is especially important in stoichiometry and in calculating the outcomes of chemical reactions. Avogadro's law helps chemists predict the volumes of gases produced or consumed in reactions. For example, in the reaction between hydrogen and oxygen to form water, the law allows us to calculate the exact volumes of gases needed or produced. This is crucial in laboratory experiments and industrial processes where precise measurements are essential. Ideal gas law combines all the previous laws into one comprehensive equation, PV equals nRT. Here, R is the universal gas constant. This law allows us to calculate the state of a gas when pressure, volume, temperature, and number of moles are all known. It's a powerful tool in both theoretical and practical chemistry, providing a foundation for more advanced studies. Ideal gas law is used to solve a wide range of problems, from calculating the amount of gas needed to fill a balloon to predicting the behavior of gases in engines. It's also essential in environmental science, where it helps model the atmosphere and understand air pollution. Mastering this law opens the door to countless scientific and engineering applications. While the ideal gas law is incredibly useful, it has its limitations. It assumes that gases behave ideally, meaning their particles do not interact and occupy no volume. In reality, real gases deviate from this behavior, especially at high pressures and low temperatures. Understanding these limitations is important for accurate scientific calculations and for knowing when to use more advanced models. Real gases differ from ideal gases because their particles do interact and have volume. At high pressures, gas particles are forced closer together, and at low temperatures their movement slows, making interactions more significant. These deviations are important in industrial processes and scientific research, where precise predictions are necessary. To account for the behavior of real gases, scientists use the van der Waals equation. This equation modifies the ideal gas law by including terms for particle volume and intermolecular forces. It provides a more accurate description of gas behavior under non-ideal conditions, making it essential for advanced chemistry and engineering applications. Gas laws aren't just for scientists, they affect our daily lives in many ways. From inflating tires and balloons to understanding how refrigerators and air conditioners work, these principles are all around us. Recognizing the role of gas laws helps us make sense of the world and solve practical problems more effectively. Meteorologists rely on gas laws to predict weather patterns. Changes in atmospheric pressure, temperature, and humidity all influence the behavior of air masses. Understanding these relationships helps forecast storms, wind patterns, and even the formation of clouds. Gas laws are truly fundamental to the science of meteorology. Medical professionals use gas laws to ensure patient safety and effective treatments. For example, understanding how gases behave under pressure is crucial in administering anesthesia and in hyperbaric oxygen therapy. Gas laws also play a role in respiratory care, helping doctors manage oxygen and carbon dioxide levels in patients. Engineers apply gas laws in designing engines, refrigeration systems, and even spacecraft. Accurate predictions of gas behavior are essential for safety, efficiency, and performance. Whether it's optimizing fuel combustion or designing pressurized cabins, gas laws are at the heart of many engineering solutions. Pilots and aerospace engineers use gas laws to understand how changes in altitude affect cabin pressure and oxygen levels. These principles ensure passenger safety and comfort during flights. Gas laws also help in designing emergency oxygen systems and pressurized cabins for high-altitude travel. Scuba divers rely on gas laws to avoid dangerous conditions like decompression sickness. Understanding how pressure changes with depth helps divers plan safe ascents and descents. Boyle's law and Henry's law are especially important in this context, ensuring that divers stay healthy and safe underwater. Athletes and sports engineers use gas laws to optimize equipment and performance. For example, understanding how temperature affects the pressure in basketballs or footballs can influence game outcomes. Gas laws also help in designing protective gear and improving athletic training environments. Environmental scientists use gas laws to study air pollution, greenhouse gases, and the behavior of the atmosphere. These principles help us understand climate change and develop strategies to protect our planet. Gas laws are essential in modeling how pollutants spread and how the atmosphere responds to human activity. Industries use gas laws in processes like chemical manufacturing, food packaging, and energy production. Controlling gas pressure and volume ensures product quality and safety. From making carbonated drinks to producing fertilizers, gas laws are a backbone of modern industry. Space missions depend on gas laws for life support systems, propulsion, and maintaining cabin pressure. Engineers must carefully calculate how gases behave in the vacuum of space to keep astronauts safe and equipment functioning. Gas laws are truly universal, extending their reach beyond our planet. Food scientists use gas laws to create better packaging, preserve freshness, and even develop new cooking techniques. Modified atmosphere packaging relies on controlling gas composition and pressure to extend shelf life. Understanding gas behavior is key to innovation in the food industry. Firefighters use gas laws to predict how smoke and gases will move in a burning building. Understanding pressure and temperature changes helps them plan safe entry and rescue strategies. Gas laws also inform the design of breathing apparatus and fire suppression systems. Transportation systems, from cars to airplanes, rely on gas laws for engine efficiency and safety. Fuel combustion, tire pressure, and even air conditioning systems are all governed by these principles. Mastery of gas laws leads to safer, more efficient vehicles and travel experiences. Power plants and energy systems use gas laws to optimize the production and distribution of energy. Whether it's generating electricity from natural gas or managing steam in turbines, understanding gas behavior is crucial for efficiency and safety in the energy sector. Laboratory experiments often involve measuring and controlling gases. Accurate application of gas laws ensures reliable results and safe procedures. From chemical synthesis to environmental testing, gas laws are a daily tool for scientists and researchers. Environmental protection efforts use gas laws to monitor air quality and control emissions. By understanding how gases disperse and react, scientists can develop better pollution control technologies and policies. Gas laws play a vital role in safeguarding our environment for future generations. Innovators and inventors use gas laws to develop new technologies, from energy storage to advanced medical devices. Understanding gas behavior opens the door to creative solutions for modern challenges. Gas laws continue to inspire breakthroughs in science and technology. Safety protocols in many industries depend on gas laws. Proper storage and handling of pressurized gases prevent accidents and injuries. Understanding the risks associated with gas behavior is essential for creating safe workplaces and public spaces. Teachers use gas laws to introduce students to scientific thinking and problem solving. Simple experiments with balloons, syringes, or bottles help students visualize and understand these important concepts. Gas laws are a gateway to exploring the broader world of physics and chemistry. Researchers continue to study gas laws to refine our understanding and develop new applications. Advances in technology and materials science often lead to new discoveries about gas behavior. Ongoing research ensures that gas laws remain relevant and useful in a changing world. As we look to the future, gas laws will continue to play a vital role in science, technology, and society. From developing cleaner energy sources to exploring other planets, understanding gases will help us tackle global challenges and unlock new possibilities. Let's recap what we've learned. Gas laws describe the relationship between pressure, volume, temperature, and the amount of gas. Boyle's, Charles's, Gay-Lussac's, Avogadro's, and the ideal gas law each reveal different aspects of gas behavior. These principles are essential in science, industry, and everyday life, helping us understand and control the world around us. Thank you for joining us on this journey through the study of gas laws. We've explored how these laws shape our understanding of the physical world and drive innovation across many fields. Whether you're a student, a scientist, or just curious, mastering gas laws opens up a world of possibilities. Keep exploring, experimenting, and applying these principles in your own life and studies.